You're listening to Würth Elektronik's What's Up radio podcast, where each week we are seeing what's up in the world of electronics and PCB design. We'll be checking in with leading industry experts and our very own Würth Elektronik specialists. We're going to shine a light on interesting topics, such as energy harvesting, wireless power transfer, EMI issues, lighting, and sensors, and so much more. Tune in to get technical design tips and applications during your commute, at your desk, or wherever you might be, with Würth Elektronik's What's Up podcast. The versatility of light, it is truly remarkable. It serves a pivotal role in really diverse applications, from fostering plant growth to facilitating cell restoration, and even acting as an effective disinfectant. Light has proven indispensable in numerous domains. Beyond its conventional applications in lighting, signaling, and horticulture, light holds promising potential in advanced sensing applications. In today's podcast, we are shining a light on the working principles of optical sensors. We'll start with a basic understanding of relevant optical material properties in applications, and then we're going to discuss the effect of external influences like incident sunlight.
The topic today is about optical sensors, and the title is Sensing with Light, and then optical sensors. So the prime goal of this talk is to show you how we can go from the existing optoelectronic portfolio, where we have already a lot of LEDs, phototransistors, photodiodes, how we go from there to optical sensors, and how we can use the existing optoelectronic components for sensing with light. So first I want to give a brief idea where you can find optical sensors in your daily life. So here on this first page I showed you an overview of a few stations in your day where you have optical sensors. So maybe you wake up in the morning, look at your phone. The phone can see if your face is there or not. This can happen with an optical sensor. Then you go to the toilet. How does it, there's this automatic flush. How does it work? There's an optical sensor inside that's detecting if you're there or not. Then maybe you know also, you've seen also those kind of infrared detectors. Those are presence sensors that, Okay, so maybe you also know those kind of presence sensors. They are actually nothing else than optical sensors. Basically what they do, they absorb the infrared light that is emitted by people, and then they see if there's someone there or not. And then maybe you go to the train station. There you know those ticket machines. For the ticket machines, of course, if you put a ticket inside, it's doing a stamp. But how does the ticket machine knows you put something inside? So this can happen also with the optical sensor. Then you're going into work. There's an automatic door. How does it know you're there? Well, optical sensor. Then at your workplace, there's maybe a light over your workplace. This light doesn't need to be on all the time. So what if there's a bright sunlight outside and actually you want to save energy inside, so you don't need the light inside to be on maximum. So there you can have a light sensor, an ambient light sensor, which is like dimming the light if there's already enough ambient light. Then on the lower left, you see a picture from our warehouse. And there you see a lot of those small boxes that go around in circles and through the whole warehouse. Of course, the system needs to know where those boxes are. So how does the system know? Well, there are some infrared-based optical sensors that check if there's a box passing by or not. And then what's going into development and more, it's going to be more and more in the future, is this automatic driving, for example. You can do automation in the warehouse, robots that are moving around boxes, but also cleaning robots. There you need a system that's avoiding collision. So you can do presence or distance detection with optical sensors to avoid them crashing into each other or into humans. Then you're going home, you're going to a parking garage, and maybe you know those systems where like there are lights over each parking lot or a parking spot, and it's showing you if there's a car already there or not. So this kind of sensor, like a display if there's a car or not, can be also done with an optical sensor. Then maybe you go to a doctor, and maybe you've seen something like this already. This is a measurement device to measure the blood oxygen. And there, like how does it work? You have basically infrared, red or green light that is going through your finger, and the device, there's also a photo detector in there that is detecting how much light goes in at every wavelength. And from this information, how much light passes through your blood or how much is absorbed, you can actually get values like the blood oxygen level. So this is a interesting application in biometrics. But then you can also use it for temperature measurements. So this is an example of far infrared light. So you can actually, those contactless in infrared thermometers. So they're actually based on the infrared emission of bodies. So I think I want to give good understanding or another approach on how to look on what is light exactly. So everyone knows what is visible light or sunlight is. This is something we see with our eyes. But actually the electromagnetic radiation spectrum is even much larger, and like the optical spectrum is much larger. There we have the UV region, and we have the infrared region, and also far infrared region. So UV means lower wavelengths than visible light, and infrared means higher wavelengths than visible light. So interesting point of view on looking on, or like trying to understand light, is something called the black body radiation. So maybe you know those old light bulbs with the filament inside, and if you turn, you turn them on a little bit, so you put in a little bit of current, then they start to glow red. If you turn them on more, they start to glow like more whitish. So what happens there is, depending on the temperature of this filament, you get a different color temperature. So you get a different light emission. And this is the idea of this black body radiation. Every body that has a temperature emits light with a different, with a certain spectrum, and then you end up with spectrums like this. And then you see, for example, an object with 3000 Kelvin appears to be like a little bit reddish. If you have this object at a higher temperature, like 5000 Kelvin, this is more like yellowish. And if you go to even higher temperatures, then it's more bluish. So just for objects in daily life, so the sun has a surface temperature of something around 5000 Kelvin, and this is why actually it appears a little bit yellow to us in the eyes. For LEDs, we have white LEDs in our portfolio. Of course, they don't heat up to 3000 Kelvin. They just mimic the light, the visible area of the light of this black body spectrum. But so what's important here to notice is, well, you have light, the visible light here, but you can also go to larger wavelengths if you cool down the temperature. So what's really interesting to see is, if you go down to 300 Kelvin, which is basically the body temperature of a normal human being, then you have emission around 10 micrometers. So actually every body that is, or like every human, emits infrared radiation, and this can also be sensed. So let's look into more detail, like what are the different application areas of the different wavelengths and light areas. So we have the UV light, that is has a really low wavelength, like 100 to 400 nanometers. It means they have a really high energy, and this high energy makes it really useful for curing and disinfection. So you can kill actually bacteria and viruses with this UV light. But the downside to it is it can damage eyes and skin because of this high energy that every photon has. Well, if we go to a longer wavelengths, we have the visible light, that what we can see with our eyes. So this is like what you normally understand under light, and of course you use it for signaling and illumination. So here you want to illuminate something, or you want to show something with light. So, and now the really interesting region is the infrared region, which is above 780 nanometers. The interesting part about it is it has a low energy, so it's not so dangerous, and it's invisible to the human eye. So these two properties make it actually very useful for sensing application, because you can use it to transmit data or sense object without like being a disturbance to the human eye. This is why a lot of sensing with light is being done in the infrared region. So I want to give a quick overview of the product portfolio we have in the optoelectronic department. Basically, we have LEDs from 275 nanometers in the UV for disinfection up to 940 nanometers in the infrared region. So everything in between we have in our portfolio. So let's go now to the optical sensors. Like, what are the principles of optical sensing? So I can divide them into like two basic principles. One is really simple: light detection. So the goal of the optical sensor is to detect how much light or how much optical radiation comes to the sensor. So a really simple example of this are the our Würth Elektronik photodiodes and phototransistors. So they basically are just detectors for infrared light. But then you can also do it like a little bit more complex. You can also put an emitter there. And when you put an emitter there that is emitting infrared light, and then you have an object, this is reflecting the light, then you can actually sense objects with this. And this is the basic principle of object detection with light. You just emit light, look what's coming back. And of course, you can already do this with existing Würth Elektronik components like infrared LEDs and as emitters, and photodiodes or phototransistors as detectors. So the future development will definitely go into the direction of putting emitters and detectors into one package and make this like more readily available or easier to use for customers. So this is the future. In the future, there will be a group called optical sensors in our portfolio as well. So I want to give a basic understanding of which parameters that we find in the data sheet for optoelectronic components are actually relevant for sensing with light, for optical sensing. So first of all, I have here in the detection side a phototransistor. So what is the goal of a phototransistor? I apply a voltage, and then it's basically detecting how much light is getting into the detector, and depending on how much light, so if there's more light going in, then the output current of this detector is going up. So it's only light to current converter. So on the other side, like if we will look at the emitter, so actually here we have an infrared LED emitter. There the basic principle is we put through a current and then look at the light that is coming out. So there's if we put more current through it, then there's more light coming out. So this is like the first basic step of the optoelectronic components. But there's like more to it. you also have to consider the spectrum or the wavelength where they can emit and detect. So in this graph, you see a spectrum, and in black is the emission curves of 850 and 940 nanometer LEDs. And in red, you see the sensitivity curves of Würth Elektronik photodiodes and phototransistors. So there, what's interesting to see is, you can choose depending on which detector you have. If you want to choose the one with daylight, without daylight filter, or with daylight filter, it's better to choose 850 nanometer LED or a 940 nanometer LED. So daylight filtering means it's filtering out visible light. Visible light means here below 700 nanometers. So actually this kind of daylight filtering is really interesting if you want to use this application somewhere where you can also have stray light from, I don't know, some light source. And in this case, you would also try to use the 940 nanometer in a combination with the black lens photodetector. If you have an application that is you don't have any problems with light coming from somewhere, then you can also use a water clear package that is not like filtering out visible light, and actually there's more light coming to this to the chip if there's no filtering, and actually you can get a better sensing result. So later we will go into more detail about this filtering, but let's look at this later. So another important parameter for optical sensing is the viewing angle. So what is the viewing angle? It's actually the angle under which, in which direction the LED or the emitter emits light. So you can imagine one LED emitting more light to the front, or an LED that's more emitting more light to the sides. Maybe it's more wider, or it's more focused. And the viewing angle is basically a measure for this. So it is this angle at which the maximum intensity goes down to half the maximum intensity. So normally for a simple surface, if you have a simple surface that is emitting light randomly, what you will end up with is a 120 degrees emission angle. So this is called a Lambertian source. It's just a surface that's emitting light randomly, and when you look at it, it gives you a viewing angle graph like this one. And this is actually the reason why most of the LEDs that don't have special optics on top of them, they have a viewing angle of 120 degrees, and the graph looks similar like this one, because LED chip is more or less just a surface that's emitting light like a Lambertian source. So, but what you can do is reduce this viewing angle, so make the light more focused, if you put on top of the chip a lens. And what happens if you put a lens in front of it, then you go from the 120 degrees, you go down to, depending on what the lens you use, maybe 30 degrees. So actually you're focusing the light much more. So it means you have more light on the spot, but of course less light in the surrounding. So you don't have such a large spot. And what you can do with this, with reducing the viewing angle, you can actually increase the irradiance. So this is the amount of light coming onto a surface. And you see here a simulation of going down to lower and lower viewing angles. The irradiation is changing by orders of magnitudes. So this actually has a huge impact on how much light gets on a surface. Fun fact, this is also why lasers are so dangerous. So lasers have a really small viewing angle, which means that the irradiance is going up really, really high. So there's a lot of light on a small area. And if a laser beam hits your eyes, then you have a lot of light in a small area, and this is what's making them so dangerous. But nevertheless, so no worries, the lasers we have so far in our portfolio, they have a really broad viewing angle, so there's no problem with this issue. Actually, they are not so dangerous. So let's look at a really simple principle of a reflective sensor. So basically, the idea is I have an emitter and I have a detector. In between, I have a light barrier, so they don't talk to each other directly. And the goal is to sense an object, if there's an object or not. Well, the main question a lot of people ask themselves is, how far can I detect this object? So like, what is the working distance here? Like, what is the useful distance, and which LED should I choose for which distance? And the goal of this slide is to show a few simulations to give a general guidance and understanding what different parameters, especially like the viewing angle and the distance, do on the detection possibilities in this kind of configuration. So yeah, so on the right-hand side, what we see is the irradiance that is coming back on the detector, depending on the distance between the object and like this optical sensor here. And like I have it once in linear here, but also once in logarithmic, because then you can see it over a larger range. So what we see here is that the irradiance, actually it's dropping down really, really fast if you go to larger distances. So in this case, I used for the simulations, I used like 4 milliwatts of radiant flux, which is something you can achieve with most of the chip LEDs in our portfolios. So chip LEDs means the low power infrared LEDs that are really small like this. And the idea was, okay, what are interesting irradiance levels, so where we can see if a detection works or not. For that, we can look at the datasheet of the photodetector. So the photodetector, the phototransistor or photodiodes, we typically measure them at 1 milliwatt per square centimeter, which translates to 10 watts per square meter. So let's say we want to build a sensor and we want to get this amount of irradiance on the sensor. Then the question is, okay, what viewing angle do I need to get a certain distance? And this is what we can see here. Let's say we want to get like 10 watts per square meter. For 100, for a really high viewing angle, we have only like detection distances of something like 10 or 5 to 10 millimeters. If we go to lower viewing angles, then we have already like 25 or even 30 millimeters of detection range. And this is like the assumption here is all of them have the same optical power output. The only difference is a different viewing angle. So this is a basic understanding. If you want to have a larger detection distance, of course, you need a smaller viewing angle. You need a lens on top that is focusing your light more. Currently, there's in development optical sensors where we want to put the emitter and detector in one package, which can look like this. And so the idea is to make this in one package, so it's like simpler to use, and it has a smaller form factor. So it's actually, you can do it like really small and miniaturization. And yeah, so there's a big need for optical sensors, like 2-in-1 packages like this. So here the basic idea is I have LED and phototransistor in one package with an optical barrier in between. The light comes out. If there's a reflecting object above it, it's coming back and being detected here. So the distance characteristics, so now those are really measured values, looks like this. So for small distances, there's some rise, but for large distances, this is actually the kind of behavior we were simulating before in this slide. So So this is quite interesting to see. So actually this, like here, this one has a really low, low power need. So it doesn't need a lot of current. And what you will see is this one is really useful for only really small distances, like maybe 1 millimeter or maybe up to 5 millimeters. So what's also interesting to see is depending on the object that I'm looking at, I get very much different output currents at the collector. So here I have once a measurement with a white card. So there's it has a 90% reflectivity, and once with a gray card, which has a 18% reflectivity. You see already a lot the difference. So actually the detection result for this simple kind of sensor will strongly depend on the surface properties, or like on the color of the object that you are detecting. But of course it will also depend on the orientation. So imagine you have the sensor here and the object here, and actually the object is maybe tilted around a little bit, then of course the light is not being reflected so nicely back to the sensor, so it's also reduced collector current, what we would see in this situation. So this is another principle of sensing with light. So the idea is not to have like emitter and detector next to each other, but to have them like facing each other. And then if there's an object coming through, I want to detect this object. So we've gotten a lot of requests in the past to see or to get an understanding of what is the actual distance you can have between the detector and emitter to make to make an application like this work. So the idea is to have like LEDs on one side, detectors here, and then if there's an object passing through, I want to detect if it's there or not. So basically what we need there is also to have a knowledge and an understanding of how much light is actually going to the detectors depending on the distance. And this is what I want to show here. So earlier we had the reflected light, now it's like direct light. So what I show here is also simulation data showing distance dependence of the irradiance. So this detector sees this amount of irradiance. And remember, irradiance on a detector means output current. So if this irradiance is higher on the detector, the output current is also higher. And this is what we are actually detecting or sensing with a photodetector. So like earlier, you see the same behavior for larger viewing angles. The distance is smaller than for smaller viewing angles. One thing maybe you've noticed this little sun here. I put this here to give a perspective on what is stray light actually doing. So later I have a dedicated slide for this, but here just for your first information. If you have a sensor like this operating in sunlight, the sunlight will do a huge disturbance, a huge signal on the detector. And what I show you here is the sunlight is actually something like 1,000 watts per square meter of irradiance on a surface if you have direct sunlight. And actually this is like 2 orders of magnitudes larger than what we have typically in laboratory environments. So you need to be really careful with sunlight, but later more on this. So another interesting question when someone wants to design an application like this, so to see this to make a transmissive sensor to be able to detect if something is going through or not. The question is, how much tolerance does this system allow? So what happens if you misplace them? So is it really forgiving? Can you misplace them by a few millimeters or centimeters? What happens if it's shaking around a little bit? So it's actually quite interesting to see, like at a certain distance, what is the tolerance that we can have in the positioning of the detector here. So for this, I have compared 3 different viewing angles of LEDs. So okay, I have a 30 degrees LED, I have a 60 degrees LED, and a 120 degrees LEDs. So now let's place a detector deliberately off center, and let's see what it sees. So if we put it here, like if we have a low viewing angle LED, then you see that most of the intensity drops already within 11 centimeters from the maximum. If you have a larger viewing angle, then at this position you have like 10% of the maximum. And if you have even more larger viewing angle, like 120 degrees, you see that it's actually you're already almost at the center, even if you're like off center. So actually having a big viewing angle can be quite forgiving with a misplacement, if this is an important parameter. But of course, what you see is the total intensity, so the irradiance is much less for this larger viewing angle. So there you won't be able to detect so far. So then there's, let's have a look at different infrared types or LEDs that can be used in, like, I want to give an understanding what is the difference between different infrared LEDs and types. So when you look on our website, you will find a lot of different infrared LEDs. The question is which one to use where. So this is why I give this overview table. And basically here I have chip LEDs and PLCC LEDs. Those are low power LEDs. They have a quite low radiant flux or radiant intensity. Different viewing angles from 30 to 120 degrees. And they are mainly used for signal and detection. So the good thing about those is that they are really cheap, really small, and you can make them flexible, like put them in different applications because they are so small. And there's of course like different typical sizes that are very common on the market. So this is for the low power chip LEDs and PLCC. But we also have higher power LEDs, so like QFN packages and ceramic packages. Those are like put out a lot of optical power, so up to 1.4 watts of optical powers. They have mainly like a little bit larger viewing angles because they are mainly meant for illumination. So they are really useful for illumination. So if you have, for example, a security camera and you want to illuminate a large area with infrared light, and this like camera should detect the like infrared light or like see a person going somewhere in the infrared region, actually those kind of LEDs are really useful because they have a high intensity, so high optical power, and they have like a big area they can illuminate. Then what's interesting is VCSELs. So VCSELs are a kind of laser that are, and in this case, our VCSELs that we have a glass on top of them that is a little bit diffuse. So this diffuse glass actually makes that the viewing angle is not very small, but it's a little bit broadened up. So actually the viewing angle is not very, very small, but like 45 and 100 to 110 degrees, depending on the part number. And so what is actually the advantage, and like why would you want to use a VCSEL? Well, it is more expensive than classical infrared LEDs, but for certain applications you want a higher power, and then you can go to the VCSEL. They can give you out a much higher power than normal infrared LEDs. And what's also important is they are much faster than normal LEDs. So actually you can switch them on and off really fast. So this is why it's or this makes them really interesting for something called time-of-flight applications. So time-of-flight application is something where you switch on the light really fast on and off, and what you're doing, you're measuring the amount of time it takes for the light to travel to an object and comes back. So there you would need something like a VCSEL or a laser that has a really fast switching time. Then there's another group that is like still in development, the optical sensors group. There the idea is to have a really small power, low form factor. So the idea is to make a small package, to have like emitter and detector in one package, but also and detect different distances, maybe some with a smaller viewing angle with a larger distance, and some with a larger viewing angle with smaller distances. So the idea is to go in the future for more optical sensors, also with, like, now I showed you like a few millimeters, but in the future also to go to higher distances. Okay, so here's another interesting illustration of different infrared emitters, to get a basic understanding what is actually the difference between them, because there's so many different, and sometimes you want to use those, sometimes not. And like it's good to know, to see how much light goes onto a surface at a certain distance, just to be able to see which emitter can do what distance. So the idea is we start from chip LEDs, which are really low power, and then go to top LEDs, and then QFN or ceramic LEDs, and then up to VCSELs so they have an increasing optical power. And the question is now, okay, what is the distance to achieve a certain irradiance? So I chose the irradiance of 10 watts per square meter. This is what typical operation values are for optical sensors, or like for phototransistors and photodiodes. And here in the red bars, you will see the distance you can, at which you achieve this 10 watts per square meter for a few selected different product numbers. And there you see, of course, with the low power, you have a really low distance where you achieve this high irradiance. But you can, with the low power, you can increase the distance when you put a dome on top, so a lens. Then you have a focusing effect, and you can reach higher distances. Then, but you can also increase the amount of current, or like optical power. Then if you increase the optical power, of course, you also get more light on a surface. And then you can do again, like with the same optical power, go to a smaller viewing angle, then increase the distance, go to higher power, lower viewing angle, and then higher power. And see, like currently our VCSELs are the ones with the most, they can give out the most amount of light per surface area at a certain distance. So yeah, here's just an overview, like different LEDs, different types of LEDs are used, can be used at different distances. So now, as promised, I want to talk a little bit more about the effect of sunlight, or like ambient light or stray light, on optical sensors or optical detection. So let's look at this graph on the right side. Here in yellow, I have the sun spectrum. What we see is it's going all over the visible range, but also very much and far into the infrared range. So the question is, what will a simple photodetector, also like a phototransistor or photodiode, see when sunlight is shining onto it? Well, of course, if there's a water clear lens, so like there's no filtering inside, then all the light, it's just getting on the chip itself, and it's detecting everything. So the amount of light that is getting on the chip is something like 470 watts per square meter. if you have a water clear lens. So this is actually what the detector sees. If you want to filter out some daylight, you use a black lens. And we, as mentioned earlier, with a black lens, you filter out visible light, so below 700 nanometers. Well, this works nicely inside, but the problem is in sunlight, there's also a huge amount of infrared light. So actually, even though this black lens is doing ambient light reduction and like reducing the visible light, it is not saving you from direct sunlight. And to illustrate that this can be a problem when designing an application, let's look at, so when we do a design of an optical sensor inside, inside we have a normally LED illumination nowadays. LED illumination looks, has a spectrum like this. So what you see is that only in the visible range you have a lot of light, but it's going down really, really rapidly if you go to infrared region. So actually, even though if you would have inside, maybe you have you test your application under really bright light inside, it's not the same as if you would test it under sunlight. So see, in the infrared region, if you have, for example, a 940 nanometers detector or like a application, then in like inside, I would barely even like detect anything. But if I go use this application outside, suddenly I have the sunlight as an emitter, which gives like several orders of magnitudes higher intensity at this certain wavelength. So this is quite interesting, and this also comes a lot as questions when someone wants to design or like is using optical sensors or like using our infrared LEDs and detectors. They are thinking, well, there's a ambient light filtering already in this black in the black lens. So actually, I don't need to worry about ambient light, and it works fine if I try it out inside. But then sometimes maybe the light shines on the optical sensors, and suddenly I have a really big problem because I see the sunlight is doing so much disturbance in the system or in the optical sensor that I didn't see even earlier. Okay, so this is something to take care of. Now I want to give a short summary. So the goal of the presentation was to show that we have the Würth Elektronik optoelectronic portfolio. We already have a lot of optical sensors. So basically optical sensor meaning phototransistors and photodiodes. But we can also use infrared LEDs for optical sensors. Then I showed you like a few basic parameters, what is relevant for optical detection. And I showed really basic examples of detection principles, ones being the reflective type and ones being the transmissive type. And also the main goal was to give a like good understanding, a few like simulations and overview that can be used later. Maybe you are sometimes in the like situation when you need to choose an LED for a certain application, and you don't know if you want it with a dome or like with this viewing angle or with this power. And I hope like the simulation data shown in this presentation can actually be useful there in the choosing of the right component in your application.
To download the slides from today's presentation, simply click the link in the description or visit us online at www.we-online.com/podcast. While you're there, you can also check out the entire lineup of optoelectronics and sensing components available at we-online.com. We understand that some videos and images are not available on all streaming networks. To replay the entire podcast with video, Visit our website at www.we-online.com/podcast or check out the Würth Elektronik YouTube page. You are listening to Würth Elektronik's What's Up podcast, where each week we're seeing what's up in the world of electronics and PCB design. We'll be checking in with leading industry experts and Würth Elektronik technical specialists. We're going to shine a light on interesting topics like energy harvesting, wireless power transfer, EMI issues, and so much more. Tune in to get technical design tips and applications during your commute, at your desk, or wherever you might be with Würth Elektronik's What's Up podcast.